Welcome to Wireless Future. I'm Eric Larsson, and I'm here as always with Dr. Emil Björnsson. Hello, Emil. How are you today?
I'm fine. How are you?
I'm good, thank you. So the topic for our discussion today is going to be mirrors that can think, or as the wireless scientists like to put it, reconfigurable intelligent surfaces. So, Emil, tell us, what is this thing?
Yes, so let us just start talking about a regular surface that is not intelligent, not reconfigurable. So in wave propagation, as we are working with in wireless, the waves are reaching different surfaces, and then you have the classical physics phenomena like reflection, scattering, diffraction, refraction, absorption, and things like that. And those things are predetermined. The surface is behaving in one particular way. And in a reconfigurable surface, we can electronically change these properties. And if it's intelligent, we can do it in a steerable way so we can adapt the propagation environment to our needs.
Right. What you're saying is that it's like a surface that you can somehow control its behavior, the way that it scatters or reflects the waves that come in. Is that what you're saying?
Yes, exactly.
I mean, yeah. So yeah, this is an exciting technology. So where does research and development stand with respect to this technology currently?
So it goes back to different types of concept of how to build antennas in the electromagnetic literature that have been going on for decades. So there is the concept of reflect arrays, which were first fixed and then they were something that became reconfigurable. And now there is something called metamaterials that can be used to build surfaces that can be controlled in this particular type of way. And in a way you can think of it that when it comes to traditional base station antennas, you can either tilt them mechanically or you can electronically change the behavior within it so that you're essentially tilting its signal. And in the same way, the idea here is that instead of having a metal sheet that you're changing mechanically so it becomes bended sometimes or sometimes not, or rotated, you change its properties electronically so that it does essentially the same thing.
Right, so you said metamaterials. I mean, that sounds like something you hardly have in the kitchen or in the garage at home. Is that like, I mean, could you tell us more? Is that like a material where that can change its properties so that the electromagnetic waves are scattered in different ways depending on how it's configured?
Yes, exactly. So it is definitely a kind of material that won't appear naturally. It has been engineered to have this kind of weird properties that you're not observing in reality. And it's essentially, you would like to change its properties, impedances and things like that on a atom level, but you can't do it all the way down there. So instead you divide it into small pieces that we call meta atoms, but they are typically a wavelength divided by 5, a wavelength divided by 10 size. And then you put many of them, and each of them have discrete properties that you can change.
Right. So do I understand properly? I mean, so the surface is like built out of, you call them meta atoms?
Yeah, or just elements, you can call them.
Yeah, elements. So like a mesh or net of elements like that. So how large are these elements relative to the wavelength?
So you would like it to be as small as possible to have some kind of resolution in how you can change the properties, but you also can't do them too small because it just becomes complicated. So wavelength divided by 5 to the wavelength divided by 10. So it's sub-wavelength sized. And at 30 gigahertz frequency, wavelength is 1 centimeter. So then it will just be down towards a few millimeters. And then it can be even smaller if you are targeting higher frequency ranges, even up to the optical range.
Right. So what frequency ranges, I mean, do we have in mind here? Where does state-of-the-art stand? And I mean, I understood that some prototypes had been developed and tested, right? So what frequency bands are they for?
So there are a number of different frequency bands that people have been considering. My impression from reading the literature is that a lot of focus have been at higher frequencies, maybe the optical range or slightly below there, what we call the terahertz range. That has sort of been the focus back in time, then now when people are starting to take this concept from electromagnetics and try to apply it in wireless communications, then we know that wireless is typically much further down in the frequency range. So there are implementation concepts also at, say, 3 gigahertz, at 30 and 60 gigahertz, the millimeter wave bands, and then all the way up in the terahertz band. So there is a number of different implementation concepts, and a few of them have also been experimentally validated.
Right, I see. So, I mean, this seems to be a very versatile technology then, right? That I mean, there are implementations, you're saying, for lower bands like 3 gigahertz all the way up to terahertz. That's a huge span in wavelengths. So is my understanding correct then that the whole concept, I mean, with these meta atoms and the surface made like a mesh of a grid of meta atoms, that it scales very well over a large frequency range? I mean, you can build this for wavelengths of a decimeter down to wavelengths of sub-millimeter. Is that so?
One thing to bear in mind is that these experiments and concepts that I was describing are mainly when it comes to actually building a surface that can do this type of things, but not necessarily that it's practical or reconfigurable. But yes, if you are building it for one frequency range, you can potentially use it also for lower frequency range, but you typically try to build it for one particular use case. And one thing to bear in mind as well is that when you are sort of trying to cheat, instead of changing the physical properties mechanically, you're trying to do it electronically, then those behaviors are only happening in a certain frequency range, and you're not making it behave in a particular way over all frequencies, as it would be the case if you're bending the surface.
One has to reconfigure the surface for a particular carrier frequency that you kind of want to reflect or scatter in some way. Yeah, got that. So how large are these surfaces? I mean, how many meta atoms goes into one surface, and how large are they physically?
So I've been seeing different types of implementation concept that people are talking about. Sometimes it's 16 by 16 or 32 times 32. Sometimes it could be, when it comes to those that are not reconfigurable, might be 100 times 100 or so. So I think there are concepts with 1,000 elements up to something like that, but many of those recent works that I've seen are more in the hundreds.
Yeah, right. So they are quite large then. I mean, you need lots of these small meta atoms to build them.
Yes, but at the same time, since they are small in terms of the wavelength, that also means that it doesn't have to be so large in size, even if you have many elements. So if one element is just a few millimeters, and then you take 20 of them, that's still not very large. And then you take it in 2 dimensions because it's supposed to be a surface. And then you can squeeze in very many in a relatively small area.
Right. So the whole idea is you can like integrate all the electronics very compactly, and when the wavelength is small, even though you have thousands of meta atoms, then the surface itself won't be physically large. As I understand.
Yeah, and what has happened in the recent years is sort of that communication engineers have taken up this idea of the meta surfaces and its reconfigurability, and thought that maybe we can just put it on the wall in our buildings and at other places, maybe at the outdoor walls, we can use them to control how the waves are going from a transmitter towards a receiver, for example, and that you would sort of cover the whole world ideally with this type of material, so you can to some extent engineer how the waves are propagating. Right.
So it's like putting up like mirrors out there, more or less, I mean, everywhere. So
yeah, and trying to build a world where the mirrors could sort of mechanically move around so that you are getting the light where you want it to be, but you do it electronically instead.
Yeah, wow, that's amazing. So where does this technology stand today? I mean, how far from being a commercial reality is this?
So I think that when it comes to actually printing such a surface, you could do that in some of these cases. The problem would be to actually build it with all of the intelligence that is needed to use it well for communications. And there is still a lot of research to be done in order to actually configure it in a fast way so that we can use them for all these things that people have in mind. So people have been saying, okay, we should use it to extend the range, or that we can use it to protect the signal from being eavesdropped from others or causing interference. And there's a lot of other ideas about how you can beamform the signal to multiple users with these surfaces in order to improve the communication. And the more advanced the idea is, the more complicated it will be to actually do it in reality. But there are a few startups that talk about this, and there are experiments going on, but I think there is still a long time before we will see something commercial.
Right, I see. Yeah. So your point here is that one has, I mean, the behavior of the surface has to be reconfigured in real time, depending on where your intended, say, base stations and user terminals are located. So, I mean, what are the physical dimensions we're talking about? Right? How far away would typically if we think like a wireless link, you have a transmitter, you might have a receiver, and then you have a channel in between, right? The ether. And now in order to enhance the radio propagation, the idea is to put one of these intelligent surfaces somewhere out there to help, to act as a mirror, to amplify or I don't know, amplify or at least help to bounce the signal towards the receiver. How far away would you be in a foreseen application? Would it be kilometers away or just meters? So could you shed some light on that?
Yeah, so I think that people have been sort of putting up ideas about all of these kind of situations, either where it's somewhere in the middle in the range between the transmitter and the receiver or somewhere else. But I think that mathematically, if you're looking into it, the ideal thing is to put it very close to the transmitter or the receiver. So it sort of acts as a big mirror that is taking as much energy as possible coming from the transmitter and then focusing towards the receiver. If that is your use case, to sort of act as a relay where you can get as much energy as possible towards the receiver. So it's a bit thinking like a satellite receiver where you put this curved surface next to the receiver antenna. And then it's very close. That's on purpose.
Right. So I read the recent papers of yours, and in the paper you claim that there are lots of myths and misconceptions around this technology. And one idea that you stated as a myth is that current network, wireless technology, cannot control the propagation environment. So it's like you deploy base stations, you throw out users with their mobiles or whatever terminals, and then it's like the radio propagation environment is something that nature gives us, right? You stated this as a myth, and that current technology cannot do anything about propagation. Propagation could be good, right? You could be in line of sight, and from your stand with your mobile, and you see the base station with your bare eyes. Or it could be pretty bad, like you're somewhere deep in a basement, and you have 30 centimeter concrete walls, and there's just no coverage. Could you elaborate on this point?
Yes. So, sort of what people will like to say is that traditionally we can only optimize what the transmitter is doing, what the receiver is doing. Everything that's in between is given by nature. It might look random to us, but it's given by nature. We can't do anything against it. And then now they would like to put up these surfaces and say, now we can create a controllable or smart propagation environment. And that will be sort of a paradigm shift called wireless 2.0 or something like that, because now you can co-optimize the propagation with the transmitter and the receiver. And in a way, you can actually do this. The problem is that this is not the first time that this idea have been put up. And actually, 10, 15 years ago when I was doctoral students, I heard people saying more or less the same argumentation, but then they were not talking about reconfigurable surfaces, but relays, which is also an equipment that you put in between a transmitter and receiver in order to improve the propagation environment. And relay idea have been around for 100 years.
Yeah, relays, have been popular, I think, research topics in academia. I'm not sure, right, that is on the spot, but 10, 15 years ago or 20, it was super hot, right? And why did this never fly? Because I have understood, very few systems or standards actually use relays to any greater extent.
So I think these standards are supporting relays. I think in 3G and 4G and probably now in 5G as well, there are standardization support for relays. The question is how often they are actually deployed in reality. And For example, if you would like to extend the coverage in tunnels or things like that, then you might use relays or repeaters or some kind of leaky cables for that. So there are some use cases, but I think what people have been realizing is that if you are going to put up an equipment somewhere, then why don't put up a base station instead of a relay?
Right, so because relays are just, I mean, almost as complicated, I suppose, and expensive as a base station, and you just get so much more value from putting a base station there as compared to a relay. Is that what happened?
Yeah, and then sort of the counter argument here would be that, now these surfaces are an entirely different story. They don't need to be so advanced, so therefore they can be used in cases where relay couldn't, and that this would sort of be still a paradigm shift. And I would like to say that if you categorize different types of relay technologies, there are like 4 different options you can see. There is the type of transparent relays that you don't need to design, change your system. They just are amplifying the signals over the air without you as a receiver need to know about it. And then there is the regenerative, that is sort of repeating the signal, so you are decoding it and retransmitting it, for example. And then there is the half duplex, where you are first transmitting the relay and then you are repeating it. And there is the full duplex, where both the retransmission and the transmission from the source happen at the same time. And among those 4 cases, there is one case that haven't been considered before, and this is the transparent relays that are in full duplex. And that is where I would say that these reconfigurable surfaces are fitting in, because they are immediately radiating the signal towards the receiver, and the receiver doesn't need to know about it. So it is a type of relay. It's just used a different terminology.
Yeah, so your point here in essence is that, well, this whole notion of controlling the propagation environment is not new. It's been around for 100 years. I mean, we can put relays, and effectively what a relay does is that it affects the propagation environment that the transmitter receiver pair is seeing, right? However, now with this like 4th generation of relay idea and full duplex and completely transparent, it might be that, well, is reconfigurable intelligent surface is the way to go and to actually implement that idea.
Yeah, it could potentially be the way of implementing relays in the future that will actually fly.
Yeah, right. Interesting. Okay. So also in your paper, you state as a myth that a reconfigurable intelligent surface achieves a better asymptotic array gain than conventional beamforming. Could you explain this in perhaps a bit more non-technical jargon, what this means?
Yes. So what is then a array gain? Well, with the typical conventional array, if you count the number of antennas in that one that are connected to radios and count them in the same way as you're counting elements in these surfaces, then what happens is that when you are optimizing how you're using your array, you focus the signal at the receiver, and you get, if you have 10 elements, you are getting 10 times stronger signal. If you have 100 elements, you get 100 times stronger signal. So say that n is the number of elements, and you get n times stronger signal.
Right, because the waves adapt like constructively, coherently, right? So you get like a boost in amplitude where your receiver stands. Yeah,
so that is the conventional array gain. And when it comes to these surfaces, what they are doing is that you're sort of, as a receiver of solar energy, the larger the surface is, the more energy you're collecting. So the amount of energy that the surface collects is proportional to the number of elements. And then that energy is then in every element you are re-radiating it, and you are sort of time delaying it in such a way that you're focusing the signal at the receiver. And then you get this type of array gain again. And if you then look at it mathematically, you sort of get the number of elements once in terms of how large the surface is, how much energy it collects, and then once again when it comes to how it's focusing it. So you will get sort of the number of elements squared. And then if you just look at those parts of the expressions, it looks like, oh, we actually are getting a much better effect. It grows in a quadratic manner with the number of elements.
I see. So I mean, from a physics perspective, right, one would think that it's the aperture size or length that matters. And so what you're saying is with this reflecting intelligent surface, then we get a gain both on reception and on air quotes transmission, because you have like the aperture gain is both for the incoming wave and the outgoing reflected wave, right? Is
Yes.
that what you're saying here? So it's like a square kind of gain, whereas with a conventional MIMO base station, we have only a gain proportional to the aperture, is only a linear gain.
Yeah, exactly.
Yeah. So why is that a myth then? That seems to me to be true. I mean,
yeah, that part of it is a myth. Is true. The myth is that this is something that would be beneficial for us. That we are actually saying that just because it grows quadratically, it's better than a linear scale. But that is not the case, because what is actually happening in wave propagation is that you lose a lot of energy from the source to the surface, and then from the surface to the receiver, you're losing even more again.
Right.
And then, yes, you're collecting a larger fraction, both in the first phase to the surface, and then from the surface to the receiver, we're also collecting more for our beamforming. But it's still like that you are talking about how much you are losing in this first step between the source and the receiver. So you can never receive more at the surface as you were transmitting. So in the best case, you are getting all the energy through there, and then you get the same performance as with the beamforming from a conventional array. While in most cases, since the surfaces are small, you are losing something along the way. How much you lose it's sort of inversely proportional to the size, but it is a loss. So one of these factors of the number of elements is describing a loss and not an improvement. So if you look at it mathematical, it means that you have two curves, one that grows linearly, one that grows faster, but that one that grows faster is always below. So they are never sort of meeting each other.
I see. So really what you're saying here is that, well, the kind of air quotes gain you get from having this reflecting intelligent surface does grow quadratically with the size of its aperture, whereas a conventional MIMO base station has a gain that grows only linearly with the size of the aperture. However, with the reflecting surface, the power that's actually impinging on the surface itself is just so minusculely small that in the end, I mean, the fact that you do have a quadratic gain theoretically makes no practical difference. Is that like a correct understanding of what you've been saying here?
Yes, but one can also turn it around when it comes to saying how will you use this surface in reality. Well, since you have this quadratic gain, sort of the larger you make it, the smaller is the loss compared to having a transmitter at the same location as the surface. So that is sort of saying that you would like to have very large surfaces, because then the technology becomes relatively competitive. And one could also argue that, of course you're going to have these losses, but we are imagining comparing a small relay of the conventional type with a large surface with this new type of technology. And in those cases, a large surface could still be good enough. But as long as you are comparing surfaces of the same size, it's the aperture that matters, and a conventional beamforming is always better.
Yeah, so I suppose because this intelligent surface doesn't amplify the incoming wave, right? It just scatters or reflects it away. So I mean, is my understanding correct that if you're comparing on one hand this large intelligent reflecting surface to a small relay, then the surface has to be very large physically in order to compete with the relay for any like practically interesting ranges of power consumption or transmission power. Is that so?
Yes. So you're sort of trading away the fact that you need to have a power amplifier that is amplifying the signal at the relay in conventional technology towards not having that, but instead you have to pay back by making the size of it larger.
Making
so this is
it
sort
large,
of a trade-off.
Yeah, right. Okay, great. So you also talk about in your paper another myth, that a reflecting or reconfigurable intelligent surface. I think people use different terminology here, by the way. Reconfigurable intelligent surface, reflecting intelligent surface, large intelligent surface. I don't know which one is the correct. I'll try to be consistent, but yeah. So you talk about in your paper here that it is a myth that a reconfigurable intelligent surface is an anomalous mirror And I was wondering if you could explain a little bit. I mean, to start with, what is a mirror? I thought a mirror is like a piece that you could look yourself in the morning in the bathroom. And what is a mirror? I mean, can we talk about mirrors in the like radio frequency domain where we use for wireless for communications? Could you elaborate on this? And what is an anomalous mirror?
Yeah, so a traditional mirror is, as you were describing, what you're looking yourself in the bathroom, a big piece of metal that is sort of reflecting your signals. And we are used to observing these type of things in the optical range, where the wavelength is 100,000 times smaller than in radio frequencies. So ideally, to have a real mirror, you need to have something that's infinitely large. But of course, approximately you can reach infinity for a smaller size, but that size that you need to talk about is something that needs to be 100,000 times larger in radio waves. So something that we are observing as a mirror doesn't necessarily need to be as a mirror in the radio frequency. But what is, when it comes to anomalous mirrors?
So Emil, let me interrupt you here. So are you suggesting that if I look myself in the mirror, I'll see myself, right? And are you suggesting that if my eyes now instead were receptive to radio frequency waves at the frequency bands that we use for communications, which means like gigahertz rather than with the visible light, are you suggesting then that the mirror I'm holding here would no longer be a mirror? It would have to be like 1,000,000 times larger? Could you amplify on that point?
To see the same type of wave propagation behaviors, you would have to rescale your world, renormalize it with the wavelength. So you would have to sort of make the surface 100,000 times larger, move away 100,000 times more, and so on.
Right. So this is an important point, I think. I mean, in physics, right? Because we think of mirrors, like we all take in electromagnetics in college, right? And the Snell's law of reflection and refraction and so forth. And these electromagnetics all assumes they have like infinitely large surface, and then you have a plane wave that's impinging on that surface, and then you can compute and prove that the angle of reflection is equal to the angle of incidence and so forth. But in reality, I mean, any physical object will have a finite size, right? And in particular, anything that we call a mirror will be finite in size. And my little mirror here is probably infinitely large relative to the wavelength of visible light. But relative to the wavelength of RF, I mean, gigahertz RF that we use for wireless, it is on the order of a wavelength in size, and it's not going to act as a mirror. It will act as a scatterer. Is that correct understanding?
Yes, exactly. And this is sort of a bit dangerous because everyone who is studying physics almost are studying this type of physics that are assuming that we are in optical range. They never really say that in the textbooks that you have an infinitely large surface. It's just sort of assumed. And in those cases, you are viewing the radio waves as being just parallel rays that are coming towards the receiver or the mirror. And those type of approximations of reality is only valid in the cases when the mirrors are large to be mirrors.
Yeah, right. So again, I mean, to reiterate this point here, what we know about mirrors from the optics class in college is that rays of light come in, and these rays of lights are reflected, right? And this is an extremely good approximation of reality. When we speak of visible light and when we speak of mirrors that are of the size that we can like hold them in our hand or even larger. But now moving to the radio frequency range with a gigahertz carrier, which means like a decimeter or a couple of decimeters of wavelength, then for any object to really behave as a mirror, it would have to be like a kilometer large. A small piece like the one I'm holding in hand here, I mean, that would not be a mirror in radio frequencies. Is this the punchline?
Yeah, definitely. And you asked earlier what an anomalous mirror is, and that is sort of a surface that is of the same size as a traditional mirror, but we are, instead of having sort of a homogeneous behaviors in the surface so that we are observing the mirror as we are used to. We have a heterogeneous properties, and those can be tuned so that you still get this type of reflection behaviors as you're used to in optics range, but you're not following Snell's law. So it's not like the angle where the signal is going out is equal to the angle where it comes in, but only on the other side of the normal to the surface. You can tune it to be something else. So that is sort of what an anomalous mirror is. And in theory, you can build something like that using this type of meta materials.
This is kind of counterintuitive. I mean, because we're all used to, thinking mirrors, right? The Snell's law, angle of incidence is equal to angle of reflection. And it would be hard to imagine or conceive of a mirror where you kind of don't see that behavior. But what you're suggesting here now is that these reflecting intelligent surfaces, because the way they are built from meta materials and meta atoms and so forth, they can be engineered to have that behavior, that the in-pinging radio wave will be reflected into a different angle. So the angle of reflection is different from the angle of incidence. I suppose that's the whole point, so you can kind of steer where the energy goes, right? And that way improve like the radio coverage. Wow. So yeah, that's a pretty amazing piece of engineering, I think, to build anything like that. So now, I also read and understood in your papers that there's been some controversy about path loss models for these reflective, reconfigurable intelligent surfaces. And I was wondering how this could come about, because to me it's like, well, it can't be controversy about anything as long as we are in the realm where Maxwell's equations are applicable, right? And classical electrodynamics describes reality well, then this is mathematics. I mean, we can in principle, always trace everything back to the wave equation, right? And how could there be controversy? Could you elaborate on this point a little bit?
So what this is really about is, the path loss of a wireless signal is saying that the signal energy is spreading out. And when we are studying mirrors, traditionally, you have these infinitely large things. And if it's anomalous or not, it's still infinitely large. And then we're studying so-called plane waves that are impinging on them, which is a theoretical idea of a ideal type of wave that is not spreading out. It's not going to become more focused either. It's just propagating in a particular direction. And then it bounces on the surface, and then it have the reflection and it propagates in another direction, and we don't lose any energy along the way. But then there are some people who are saying, well, let's now look at this reflection and let's count the total distance. And we say, okay, the wave have propagated to the surface, and then we add the distance from the surface to the receiver. Then we put this into a propagation formula like Free's propagation law, which is not for plane waves, but for a point sort that is sort of spreading out in all directions. And then we are claiming that, this is the type of path loss that we're going to get. And then we're sort of mixing up two different things, the propagation of spherical waves, which we have in reality, and the propagation of a plane wave that could, if it's ideal, you have a large mirror, can behave in a particular way. And then you can come to very weird conclusions.
Right. So is my understanding correct here that if you want to model path loss, or really if you want to model the influence of a reconfigurable intelligent surface on the path loss, viewing it as a mirror, then that might be fine if the surface itself is large enough, right? Large relative to the wavelength and reasonably large relative to how far away the transmitter and the receiver are. So that might be okay to view the surface itself as a mirror. However, the small meta-atoms that make up the surface, they are so small that they themselves cannot be well modeled physically as mirrors. They have to be modeled as scatterers. Is that a correct understanding?
Yes, so that is sort of what you need to utilize in order to compute the actual path loss expression for something like this. And it's also, there is something called the Huygens-Fresnel principle, which tells us how we could look at the signals that are scattered from a surface. So you sort of are dividing the surface into small pieces, and in this case it matches very well with the atoms that we're having, and then we are watching each of these elements as a sort of an antenna that re-radiates the signal with the energy that came in there, and then you take the constructive and destructive interference pattern of all of these elements, and you see that, okay, you're going to form a beam in certain directions and not in other directions, or focus a signal in certain directions, and it all has to do with the traditionally with the surface, you just count the propagation delay, and then you determine where will you get that signals are adding up constructively and where will you have something else. And what these surfaces are really doing is that it is sort of in each element you're time delaying the signal in a particular way, so that you could sort of reshape in which directions you are getting constructive interference and where you are getting something else. And in that way, you're sort of approximating the shape of the surface in a different way. But this is really what you will need to do to get the right path loss. You're dividing up the surface into small pieces, you apply the rules that you were describing, and you're using the possibility of time delaying the surfaces to get, or different elements in different ways to get different phase shifts, and in that way you get constructive and destructive interference. You sum up all the elements, behaviors, and you get your path loss.
Right. So, I mean, it seems the physics here is no magic, right? It's a superposition principle.
Yeah.
So you have all these meta-atoms, and you compute for each one a green function, and then you add them up, and you basically get your far field or whatever, your radiated field. Yeah. Okay. Yeah, great. So,
but there's an important thing here as well, I think, to remember, that there are cases where you can actually operate your surface to provide approximately anomalous reflection. But that is just one of the many things you can do, because if you really want to optimize the signal energy, sort of if you view it as being an anomalous reflection, you will use the possibilities to sort of rotate mechanically the direction of the surface so that Snell's law are applying, but you do it electronically. But what you can really do if you optimize things is you're changing the entire shape of the surface in the electronic domain by changing these different phase shifts. So that means you can synthesize any object having the same size. It could be the scattering of a bended or curved mirror, for example. In that way, you can get much more energy towards the receiver if you do something else than trying to approximate mirrors. So it's just misleading to try to use these surfaces to behave as mirrors, at least when it comes to plane mirrors. You would like them to be bended.
So what you're saying here is that, I mean, one way of operating the surfaces is to have them behave as an anomalous mirror that just reflects the signal into a different direction, right? You could also configure them to behave like a parabolic reflector or something else that would like focus the signal into some point where you want it to end up. Wow.
Yeah, and like a flat mirror is sort of focusing the signal at the point infinitely far away in a particular direction. That is sort of the focal point of the mirror. And if it's curved, well, then you can focus it at a much closer point where the receiver is, for example. Right. So that is something that you prefer to do all the time, if you can do it.
Right. So how is the control of the operation of these surfaces going to work? I mean, I had come to understand that each one of these meta-atoms that the surface is built from could be like controlled individually, and then it occurs to me that if you have a surface made of thousands of these such meta-atoms, you'd have to control each meta-atom individually. And how do you do that? I mean, wouldn't this require huge number of amounts of electronics connected to the surface? And how does the surface know, perhaps more importantly, where to scatter off or where to reflect off the incoming wave? I mean, it would have to know where the base station is located and where the terminals are located. Is that so?
Yes. So if we start on how it would actually operate, then every element, ideally you should have sort of a continuous change in what type of delays you can put to the signal there. But in reality, you sort of typically have a few different options, and then you can build this in many different ways. So there is not one that is the correct way. You can have some kind of phase shifter, you can have some kind of delay lines that you can tune the length of them, and you can have some diode that is controlling these type of things. And so there are many different ways of implementing it, and some of them can control every single atom, and some can just control a group of atoms, and sort of you are applying the same type of control to them. But I think what is important to remember here is that, yes, you can build some of these basic functionalities, and there are experimental results on that. But the question is really, how do you control it in real time to do any of the things that people in the communication area is envisioning? And that is sort of the complicated thing.
Right. Yeah. I mean, that sounds immensely complicated, right, to make this work. I mean, it sounds like we in the wireless comms or comms theory community will have work to do for the next 20 years to build this in reality and make it work. So, Emil, to wrap up here, what is your assessment of this technology? Will it be the next big thing? I mean, are we going to see for, say, 6G surfaces like this all over the place? I'm thinking of, was it the Castle of Versailles, where there is like a large room with mirrors, with the walls covered with mirrors, or was it somewhere else? But I mean, is that the vision for the future here, that we would see these reflective, intelligent, reconfigurable intelligent surfaces mounted all over the place? Everywhere we go, we'd see one somewhere that would track us and reflect the radio power towards us? Or what do you think?
I think that it's an exciting research topic for academia to be involved in, and that sort of the vision that many people are putting forward is to build a room like the mirror room in Versailles, where you are sort of covering the entire world in controllable mirrors. But there are really two very important research questions that needs to be answered before we can say if this will be something that can be practically used in any future wireless standard, or if it's just a nice theoretical ideas that you could think about in academia. And the first one is really, what should you use it for? Because yes, you can definitely build something like this that could reflect the signals in a particular way. We can already print them, and if you send an engineer there and control it, well, then you can do whatever kind of wave propagation behaviors that you would like to have. Scattering, reflection, change polarization, a lot of different things. But what will it be inherently good at? Because if people should invest their time and money in particular when it comes to developing product into this, there must be something that it's very good at doing, something that conventional technology cannot do. And there's a lot of ideas about what this could be. It could be this kind of relaying behavior. It can be sort of protecting a premise so no one can eavesdrop on your wireless signals. It could be handling interference in a situation so you can have more users sharing the wireless services. But I haven't seen any really convincing use case where you can do something that is, say, 10 times better than conventional technology. So for all these different use cases that I mentioned, there are other competing technologies, and it remains to really identify this is the key use case, or the first key use case at least, where you can do something that is fundamentally much better than conventional technology to put the effort into building stuff like this.
Right. So it sounds a bit like exciting new theory and technology looking for a killer application to where it can really make a difference.
Yeah, so you shouldn't really have a hammer and a mirror on the same place, but this is sort of a hammer is the tool, this surfaces, and you're looking for a nail now that you could, it can be ideal on hitting, and we haven't really figured that out yet.
Right, so a nail to drive right through the mirror. Okay, great. Yeah. So, yeah.
But then there is a second question as well, and that is, how quickly can we optimize something like this? Because there are already the idea of putting up kind of metal sheets in tunnels, for example, or you can put it on the top of a hill so that you can improve the wireless connectivity in the valley below it, for example. This is something that is used in reality to improve coverage in a totally passive way. But if you would like to use this to actually control the propagation environment, how quickly can you do it? Can you do it in real time? Can you handle users that are moving around? So as you move around, the service is continuously changing how it's reflecting the signals towards the point where you are, and in that way improving your coverage properties. And the really problem is that the service is made to be passive, so it doesn't observe the signals. It is just scattering them in a way that you can control. So then you need to somewhere else observe the propagation environment sort of learn how the signals are propagating right now, you need to try out a lot of different options. The larger the surface is, the more options there are to try out. And then you need to co-optimize that with your transmitter and receiver to utilize this smart propagation environment concept. And then you need to tell the surface about how it should operate right now. And then next milliseconds, you might need to change it again if you would like to handle mobility. So this is really, how can you do this in a resource effective manner so that it actually are working in real time and just not something that you put up once and then it will work forever, but only for very small use cases that are predefined.
Right, so that seems like the grand challenge here to to build electronics and figure out algorithms that can reconfigure this surface fast enough in real time so that, like you said, every millisecond the propagation might have changed and the direction to the, if there's a mobile user, it might have changed slightly and then you need to reconfigure all these atoms.
Yeah, exactly. Wow. And there is this connection towards the massive MIME area that we have been talking about before. So in the millimeter ranges, a lot of people are talking about that you're going to do beam searching, which is sort of that you're looking around, try out different directions, and then you see which one works. It's a bit like taking a binocular and then you look around and you know how hard it is to focus it on the right point. And the more elements you put in your surface here, and it's supposed to be large, the tinier will be your viewing area every time that you point something. So it becomes more and more complicated to search around for this. So it is really a research challenge. And before we have figured out how to deal with this, it's impossible to say how costly will this technology be, how energy efficient will it be, because a lot of overhead will have to be in learning how to point the beams here. So whenever people are saying, oh, this is going to be much more affordable and energy efficient than other technologies, the answer is that we have no idea so far because we haven't made this important piece of technology yet.
Right, yeah, great. Okay, I think we'll be closing up here shortly. Thanks, Emil. Thanks, everyone, for watching and listening to Wireless Future. As always, we'll be happy to take comments and suggestions for topics to discuss. Write to us. You'll find the contact information on our YouTube channel. And with that, thanks a lot, everyone, and bye-bye.
Thank you.